I'll try to text DJ and see what's going on with him. I think I've got his number.
Okay, I'm recording now. All right. Well, maybe some people will pop in. Anyways, get going. So this is a chapter 21 lab. And, as I began chapter 21, I discussed a couple of different experiments that were performed by Michael Faraday himself. And those experiments, the results of those experiments there's no way to explain them prior to the coverage of the material in chapter 21. And so to kind of put it in my drawing skills are always challenging, but Faraday noticed galvanometer here. As you set up a loop, a wire loop, and one thing you'll notice on this wire loop, like any material, has a resistance associated with it. Okay, I mean there is a resistance in the wire loop. Okay, so we can kind of think of there being a resistance R of some sort in the wire loop. I mean, it's made out of some material. Unless you're a superconductor, you have resistance. So here, and notice there's something missing in this wire loop that is peculiar, and that is there's no battery. I don't have an EMF in this wire. I just have a wire that's shaped like this. I have a loop portion, and I have a galvanometer. And remember what a galvanometer does. A galvanometer measures current. So why would I possibly have a current? Well, what Faraday did is he imagined for a moment, I'm just going to make a dashed line here through this, supposed to be through the center of the loop. And we have a magnet that'll be approaching this wire loop. Imagine going, straight down the middle. I mean, again, my drawing doesn't do any justice here. This magnet is going to have a velocity v. All right, so I am moving this magnet, let's say north face first, through this wire loop. And an interesting phenomenon occurs. As I move this magnet toward the wire loop, an induced current occurs. So again, as I move this magnet toward the wire loop, so I don't know how it's okay. As we move the magnet toward the wire loop, a current is induced. So as I'm moving this magnet, again, I'm going north pole first, a current is induced. Now, if I stop moving the magnet, the current stops. So if we stop moving the magnet, the current stops. I'll call it the induced current stops. All right. The faster I move the magnet, the greater the current. Again, I'm moving the magnet toward the center of the loop. All right, and so the magnet moves toward a wire loop. A current is induced in the loop. So again, how would that current go? It would go as a sight along the magnet. It would go counterclockwise. Okay, I'll explain that in a moment. So again, as we stop moving the magnet, the induced current stops. The faster I move the magnet, the greater the induced current. Interesting. And if I were to pull the magnet back, I would also induce a current, but it would be going the opposite direction. All right, and so again, more experimental results. If we pull the magnet back, or pull the magnet in the opposite direction, an induced current in the opposite sense occurs. What I mean by that is, well, as I move the magnet toward the wire loop, I get a, if I imagine sighting along the loop, I would see a current that's going counterclockwise. However, by pulling it back, I would actually see a current that is going the other direction. It'd be a clockwise current. Okay, and the faster we pull the magnet out, the faster this induced current in the opposite direction, in the opposite sense. Okay, so again, these are just experiments that Michael Faraday performed. Now, turns out if I were to do this same set of experiments all over again, but I were to move the magnet and turn it end over end, instead have the South Pole coming first and then the North Pole, all my experimental results will be the same, except all the currents will be the opposite sense. So again, if we approach the loop with a magnet, South Pole first, all of the previous results will be the same. Except all currents would be reversed. Every current I mentioned earlier would be in the opposite direction. Lisa, you have a printer? Okay. So all those results would be again the same. So again, that's one set of experiments. And again, this is performed by Michael Faraday. Okay. Now we have another set of experiments he performs. Again, we're really challenging my drawing skills now. So I'm going to take the magnet away. Now what I'm going to do is I'm going to try to draw another loop that's going to go face to face with this one. I probably should have drawn this picture before I started the Zoom session because, all right, here we go. Let's see how well I do. Try to imagine another loop right behind this one. This one, on the other hand, actually has a battery. Yeah, a battery attached. And then it's gonna go face to face. So so the idea is this loop is face to face with the other loop, right? So again, this is 2 loops face to face. Okay. We have the loop from before. With no battery. And we have the loop. We have a new loop with a battery. Now, imagine that I'm going to put a switch on this. So somewhere along here, I'll open up a switch. Again, I know it's a trouble drawing, but I'll say this is switch S. All right, so now, so the idea is the second loop is open. There's no current. And I can understand the current, let's say prior to chapter 21, I can totally understand why there would be a current in this other loop. Now, why would there ever be a current in, again, in the one that just has a galvanometer? But anyway, right now the second loop is open, and there's no current flowing anywhere. Now I'm going to flip the switch on the first loop, and what I'm going to notice is that when I flip the switch, I'll have a very temporary deflection of the galvanometer in the other loop, and then it'll go back to 0. And I'll let that current run for a while, and then I'll open the switch, turn off the other loop, and I'll see a very quick deflection of the galvanometer in the second loop going the other direction. Very momentary deflection. So what would possibly cause a current, an induced current in this second loop? Well, there's no explanation prior to chapter 21. So the idea is that something is changing. And if we go back to my lecture, the thing that's changing is the magnetic flux in the secondary loop. So let me kind of go back to my original picture. I think I drew that one better. So I have the picture, for instance, of the wire. With just the galvanometer. And here's my magnet. So what's happening? What is occurring when I have the magnet going toward the loop? Well, what's occurring is the magnet has magnetic field lines that emanate from the North Pole, go through the loop, come back around, back to the South Pole. So magnetic field lines are going to come through here, and maybe this one misses, but this one comes through, this one comes through, and maybe some of these other ones misses, and here's maybe one out here that just comes straight back. Anyway, the magnetic field lines are increasing in time as the magnet approaches the loop. As the magnet approaches the loop, the number of magnetic field lines increases per unit time. Okay, that's what's occurring. And again, it doesn't really matter how big the magnetic field is. It's as long as it's changing. All right. So what's actually occurring here is that we derive basically not derive, but Faraday understood for the first time a new law of physics, that there is an induced EMF in the coil in this loop that doesn't have an EMF. We're having basically a fake battery set up. It's an induced battery, if you will. It's like a battery would be set up in this loop right now, and it's equal to negative change of magnetic flux with respect to time. The magnetic flux, now generally if I have a nice, now these magnetic fields are not uniform. So yes, the lab tells you the magnetic flux is just B times A. That's just B times A if the magnetic field is uniform. What I really have to do is take this area and divide into little tiny areas. Area 1, area 2, area 3, area I. And what I have to do is the magnetic flux, like any flux, this is going to be a vector dot product with an area. But if I don't have a nice uniform area and a nice uniform magnetic field, what I have to do is I have to divide the area into little tiny patches. And what I really have to do is sum up over all of those patches, sum over I of the magnetic field at location I, dot product with the area at location I. And remember, in physics, area is a vector. And again, this is a dot product. All right. And it's the same as saying that it's a summation over I of the magnitude B sub I times the magnitude of the area times the cosine of the angle between the magnetic field and the area at location I. Again, these are very small areas, differential areas. And in fact, to do this job perfectly, you would require integral calculus. You have to add up the calculus style, and you'd have what's called a surface integral. This would be calculus 3. You have a little circle here saying it's a surface integral. You're adding up calculus style, and it would just be the magnetic field dot product with a differential area. That would be the way to really do it perfectly, right? But here we imagine, what are we doing in this fancy notation? Well, in a differential way, we are just dividing into little tiny dinky areas. Each area has a normal. And we're taking the magnetic field, they're taking the dot product with the normal and adding all those up. This is a scalar value. And yet the law of the universe says that as this magnetic flux changes with time, an induced EMF, doesn't say induced current, it says induced EMF. So if I have a closed loop, then I get a current, just like when I threw the switch on that other circuit. Yeah, I had a battery there, but unless I actually close the circuit, I'm not going to get a current. So if I decide to take a pair of scissors and cut this loop, well, yeah, I can have an induced EMF, but I'm not going to have a current because I have an open circuit. So in order to have an induced current, I have to have a closed circuit. I'll get an induced EMF no matter what. That's what Faraday's law tells you, is you have an induced EMF. Now, and there's no other explanation as to why that is true. This is one of the 4 Maxwell equations. Okay, it is a law of the universe. It is a fundamental truth of the universe. It does not have to be so. There's nothing that says it has to be so. It is a fundamental law of physics, that this behavior is always true. It is one of the 4 fundamental behaviors of electromagnetic theory. All right, so that's Faraday's law. But one of the questions, again, this is Faraday's law. But one of the curiosities here, or peculiarities, if you will, is why this negative sign? Okay, I've been kind of like not talking about the negative sign, but the negative sign is a statement of what is called Lenz's law. Okay, so Lenz was a German physicist. I remember his name is Heinrich Friedrich Lenz. So he was a contemporary of Faraday. So Faraday's law came out in 1831. Lenz wasted no time. He explained this negative sign, what we call Lenz's law, in just 1834, just 3 years later. Yeah, Maxwell put everything together in around 1870 to give you the first electromagnetic theory. All these equations were known about, but nobody could put the puzzle pieces together to figure out what makes the electromagnetic theory. All right. So Lenz's law says that the induced currents will work to oppose the change that created it. All right. So Lenz's law will say, again, Lenz's law, Faraday's law talks about an induced EMF. Lenz's law talks about an induced current. So Lenz's law states, so basically an induced current is generated to oppose the change in magnetic flux, the time varying change in magnetic flux, or we'll say the time varying magnetic flux. So whatever is causing this to change, it wants to oppose it. All right, so that's what Lenz's law says. So if I am moving let me erase some of this stuff. Let's say I'm moving a magnet toward the, let me just clean this up, make a new magnet here. I'm moving the magnet toward the loop. So what's happening is Lenz's law wants to oppose that. Lenz's law says, I don't like change. I don't like it at all. And I want to oppose any change that comes to me. All right. So what's that change? Well, if the magnet, north pole first, is coming toward the loop, here's the velocity vector. Well, what's happening is you're seeing a greater and greater amount of magnetic flux coming toward the loop. You're seeing a greater amount of magnetic flux coming this way. Lenz's law says, oh, I don't like that. I want to oppose it. I want to create my own North Pole, and I want to basically oppose the North Pole that's coming toward me. So I'm going to create a North Pole. So remember, in the right-hand rule of magnetism, there's always a straight part and a curly part, right? Your fingers curl and your thumb points straight. So you point your thumb in the direction of opposition. So for instance, the North Pole is coming at you, coming toward you, coming toward you. What do? Well, you want to oppose that. So you make a North Pole out of the loop. North Pole, I'm going to oppose that. Well, if I'm pointing in the direction of opposition, my fingers are going to curl in what way? They're going to curl in a counterclockwise manner if I am sighting along the magnet. If I have my eyeball right behind the magnet, I would see a counterclockwise current. The current would essentially be counterclockwise to give me a magnetic field that is opposite to the magnetic field that's coming toward me. So I have an increased magnetic field coming toward me all the time, coming toward me, increasing. I don't like that. Lenz's law says I don't like that. I'm going to oppose that with my own magnetic field. And for me to do that, for me to oppose my own magnetic field, I'm going to point my thumb in the direction of opposition. My fingers curl in the manner of the current, all right, by the right-hand rule. So my fingers will curl in the direction of the induced current. The current is only induced as long as there's a change. If you stop moving that magnet, you don't get an induced current anymore. You only get an induced current if the magnet moves, if the magnetic flux, more specifically, if the magnetic flux in this loop is changing. Now, if you decide to pull out the magnet, what happens now? Well, again, what happens at that point is the magnetic field lines become fewer and fewer. You're reducing magnetic field. Again, Lenz's law says, I don't like that. You're taking away my magnetic field. I'm going to oppose that by creating an additional helper, magnetic field to oppose what's being reduced. So I'm going to create a magnetic field in the direction to try to help out to keep the current at the status quo. What are my fingers going to do now? They're going to curl clockwise. That means my current, you'll see the current shift. Now the current in the loop is clockwise. Again, always opposing change. Now the magnetic field, now the magnet's going away. I don't like that. Magnets going away. It means that the magnetic flux is being reduced. I'm going to help out by adding more magnetic flux in the direction. I want to add more magnetic flux this way. How do I do that? Well, I induce a current by Faraday's law. I induce a current by Ampere's law. I induce a current that's going to help that additional magnetic flux. So again, this works in accordance to Ampere's law. Okay, so again, if I have a current going around a loop, what happens? You get magnetic field, right? That is Ampere's law. That's Ampere's law and Faraday's law working together, right? Because the induced current is because of Faraday's law with, Lenz's laws and interpretation on direction. The fact you have an induced current, which gives you a magnetic field perpendicular to that current loop or that current phase, that's Ampere's law. All right. So again, Ampere's law and Faraday's law working together. But that is Faraday's law saying, I don't like that reduction in you're pulling a magnet out. I don't like that. I'm going to do what I can. I'm going to create a magnetic field with the help of Ampere's law. But the fact that I want to do that, that's Faraday's law. Okay, so again, there's a lot going on with this experiment. Now, again, if I go and turn my magnet end over end, I turn my magnet end over end and say, well, instead, I'm going to instead approach it south pole first. Well, what's going to happen here is that, again, the magnetic field is coming from here, always coming out from the North Pole, going into the South Pole. So again, your magnetic field is coming the other direction, right? And the way magnetic fields work. And so you're still going to have, the closer you are, you're still going to have an increased magnetic flux. It's just going to be everything going the opposite way. And so all of your currents will be the opposite. So again, if you're approaching with the South Pole further and further, well, what's happening is you're actually increasing the magnetic flux, but you're increasing it this way, right? You're increasing it this way because the magnetic field lines are backwards because you're closer and closer. So you're going to have more magnetic field lines that are coming from the North Pole going around to the South Pole. And so you're getting more and more magnetic field this way. You want to oppose it. And so you're going to oppose it by essentially employing, you're getting magnetic field going the other directions. You want to oppose it by basically making the clockwise current this time. So the opposite of what you had before. So everything you did before is opposite, right? So again, that is just because you're opposing magnetic flux. All right. And so in the experiment, we're going to see that we're going to have a loop and we're going to have a voltmeter. And the voltmeter is just going to essentially give you a polarity of which direction your current's going. And, it'll tell you your current's going in one direction or another direction, depending upon, and so I'll kind of tell you how to predict that deflection. And we'll see how the current deflects. We'll move a magnet toward the loop and move a magnet away from the loop. So one part of this, the experiment we're going to do is going to show you the magnet going through the loop part of Faraday's law, and the other part of the experiment is going to be the part where we talk about a current, basically essentially being a time varying current loop that's inside of another loop. All right, and so again, we would actually do these very experiments face to face if we're meeting. These are really some of the most important experiments in the history of humankind. You may not see it, but the reality is, as you've been following along in the class, we talk about transformers. Well, a transformer operates according to Faraday's law. Okay, and we need to have electricity transported at very high voltages. If we transport electricity at very high or have transmission lines at a very high voltage, we reduce I squared R heating. We reduce the I squared R losses. You don't get that same, and so you only get, like, say 0.2. And I worked an example out in the lectures. For long transmission lines, you'll get about, if you're very, very high voltage, you'll get maybe 0.25% losses if your voltages are significantly lower, then you'd get maybe like 16 to 20% losses, which is not, economically, that's not good enough. So the problem is, yeah, you have to transport electricity through long power lines. I mean, again, it's a lot cheaper to have one large power plant serving a large area than having a bunch of little power plants everywhere. The economy of scale says you want one large power plant. And so you have to transport electricity long distances. And so for you to do that, you're going to have to transport them to reduce losses. You're going to have to transport them at high voltage, which means that by the time it gets to your house or your business, you have to use a step down transformer to step down the voltage to a safe level for you, like 120 volts out of the wall, 120 volts AC in the United States and Canada and Mexico. And in Europe, it's usually around 240. Other places, Australia, New Zealand, other places have like about 240. But anyway, look at it, it's a 120 or 240 is a lot less than what's being transported on the power lines. So you need a transformer. Well, remembering our study of transformers only work based on Faraday's law. Faraday's law requires a change in magnetic flux. You're not going to get a change in magnetic flux with direct current. You will with alternating current, because the current is always changing, sinusoidal. That change in current means that you always have a change in magnetic flux, and hence you have a transformer that is able to operate. So again, we run our entire world on alternating current because of this. And so our whole world, pretty much almost everything that powers your life is run on Faraday's law. So Faraday's law is the law of technology. That's the law that gives us power. All right. So that's what this lab is about. So really, this is one of the most important laws of all of physics, and I would say of all of science in general. This is one of the most important things you'll ever study, because it basically operates your life. So let's one more thing. Now, Lenz's law is also a statement of conservation of energy. So let me redraw my picture one more time. So Lenz's law is also a statement of the conservation of energy. So what do I mean by that? Well, let's imagine here, okay, so again, drawing my impoverished looking picture. All right, here's my loop again. And all right, so if I asked you, let's say you hadn't taken physics 1 yet, and I asked you a real silly question. I said, if you're on a ladder and you drop a hammer, what's going to happen? Well, if you hadn't had physics 1, you would say, oh, the hammer's going to fall. And I might ask you, well, why is that? Well, it always has in the past. Okay, I mean, fair. But now you've taken physics 1. I ask you that question again. I would expect a better answer. And so you might say, okay, yes, the hammer falls because it has a certain amount of potential energy with respect to the ground. And so as the hammer is falling, the potential energy is being lost, the gravitational potential energy is being lost, and at the expense of gaining kinetic energy. And energy must always be conserved. And I would say, okay, that's a good answer. Now, wouldn't you be surprised if, let's say you're on your ladder and you let the hammer go and it goes straight up, accelerates upward? You'd be surprised no matter what, whether you had physics or not. But there's something that's wrong with that picture. And what's wrong is you have potential energy and kinetic energy increasing at the same time. You can't have that. It's a violation of conservation of energy. So imagine for a moment that Lenz's law worked the other way. Instead of opposing me, let's say it helped me. Let's say that instead of having a North Pole coming to meet the North Pole that's approaching, let's instead imagine that I'd be met instead by the loop creating a South Pole. Then what would happen? Well, all I'd have to do then is just give it a little nudge, just a little tiny nudge, and that magnet would get sucked right on into the loop. And I'd be getting something for nothing. And you don't get something for nothing. And the thing is, when you have the North Pole going into the loop, what happens? Well, you get the induced current, one way or the other. Whether Lenz's law works the way it does, or it works in our little hypothetical universe, you're going to get a current induced in the loop. Okay. Now the current, we understand, the loop has a resistance R. And I proved this in the lecture. We had there's a example of a person pulling a rectangular wire out of a magnetic field, and there's a mechanical work, and I showed you mechanical work equals the rate of mechanical work, or the mechanical power is directly equal to the thermal dissipation power, right? And so we find out that there's two forms of energy that can come into and out of the system. So we can input energy into the system by performing mechanical work. Or we'll say mechanical power. So we can input energy into the system by doing work over a per unit time, by performing mechanical power. The system, the wire loop, dissipates the same power, the same amount of power via power equals I squared R. All right, and I prove that in the chapter 21 lecture when I talk about pulling the rectangular wire out of the magnetic field. So there is a balance of power, and there has to be. You're going to pay by doing mechanical work. You're going to have to work against some opposition. You're performing work against the opposition that the wire is going to give you, the magnetic field that it's going to induce. And at the same time, the current that's being induced is going to allow the system to actually expend that extra power through thermal energy, thermal dissipation. So the amount of mechanical power that you do to put the magnet into the loop is equal to the amount of power that's dissipated through I squared R. Okay, the two are always balanced. All right, and so if things work the other direction, you would be literally getting something for nothing. I would be doing no mechanical power. I would just nudge the magnet, it would get sucked right on in there, and I'd somehow be getting a bunch of dissipated power for nothing. I would literally be getting something for nothing. I'd be getting all that dissipated power by not performing any power, any mechanical power myself. So that would be a something for nothing situation, which doesn't happen anywhere. Okay. So yeah, we're going to be talking about that in the lab as well. So before we get into the lab, do we have any questions? It's kind of a review of chapter 21, what we need to remember for this lab. So let's look at the lab itself. Let me pull my copy of the lab out. All right. I will share my screen. There's not a lot of data per se to write down here. There's a lot of observation and discussions in this. Let's see here. All right, I just fired it up. Let me share my screen. All right, so I'll just kind of follow through what Dr. Edmonds wrote down here. Let's see here. All right, does everybody see the a magnet in front of you? Magnet in the loop?
Yes, we do.
Awesome. All right, so following through what Dr. Edmonds says, I mean, that's the initial thing. He wants you to select what's called a pickup coil. A pickup coil is this coil here. You can either have it attached with a voltmeter or this light bulb. We're going to use both in this lab. And so what we want you to do is he wants you to select the pickup coil tab, check the show field. Okay, that's already checked. Check the show compass. We're gonna have a compass. It's gonna appear on the momentarily. And there's always a delay with. Here we go. Wow, it took a while. And then we're gonna do. Oh, it went away. Goodness. All right. All right. There, show compass should be coming up. There it is again. And then we're gonna show electrons. And the voltage indicator. Okay, we're going to select the voltage indicator. Well, and show electrons in the very, very bottom. That's already selected. All right, so the light bulb went away. We now have a voltage indicator. What I want to do is actually reduce it down to just one loop. There's two loops here. So we really reduce it down to one. Now, remember Faraday's law in general. You go back to the whiteboard briefly. Faraday's law in general, you can have multiple loops of wire, right? So Faraday's law in general is that the induced EMF in the wire loop is negative capital N delta phi sub B with respect to T. All right, N is the number of loops. Okay, so the more loops of wire you have with a certain current, the greater the greater magnetic flux. Magnetic flux adds. So what you saw was two loops of wire. I reduced it so I can kind of show you a little more easily how that voltmeter works. Okay, so the initial picture you would have N equals 2 on that, but I'm taking it down to N equals 1 for the moment. We're gonna be changing that amount. So anyway, that is your general Faraday's law. Okay, you multiply by an extra factor N to account for the number of wire loops. All right, so then we want to kind of move things around kind of to match that picture that we see. So I'm going to move the wire a little bit. And I have a delay pretty much in everything that I do. I think Zoom. Well, this software is kind of hard anyway. It's all touch software, but there's a very significant delay in everything that you do when you move it. So it's a little bit of an annoying lab to do. So you don't know if you grab the item or not. I'm just trying to move the compass, right? So bear with me a little bit. It's gonna be a little challenging. I just want to try to put the compass roughly where I'm trying to match the picture that Dr. Edmonds has here. And then we have the magnet that's going to be about, it's going to be north face first. Okay, go a little closer. Okay, so here we go. So we have we have one loop. That's our setup. All right. So now we're going to look for magnetic flux and Lenz's law. So what we're going to do is we have some ability to control the magnetic field strength, for instance. So we want to set the magnetic, we want to set the 100% of the loop area. So I have the loop area right down here. It's set at 50% right now. I'm going to make the loop bigger. We're going to set it to 100%. It's going to do that slider bar. The loop's going to get bigger. And I want to set the magnetic field strength to 100% as well. So that's up in the top. So let's get the maximum strength magnet and the maximum area. So we're going to maximize our flux, okay? All right, so the coil area is A, and the strength magnetic field is B, all right? So like we normally would in physics. So number one, bottom of page, I'm on the bottom of page 1. 1 says, is the magnetic field through the coil uniform? Can you guys help me with that? Magnetic field through the coil uniform. Take a look at the magnetic. So those little arrows represent magnetic field. So the arrows are actually, as I pointed out earlier in the little lecture we just did, the arrows are not uniform. As you notice, they're all changing directions. Uniform means that not only is the magnetic field going through the loop area the same strength, but it's also the same direction. See, all these directions are different. So again, you know, if you're just to do B times A, you know, for the magnetic flux, well, B times A is only good if the magnetic field is everywhere uniform. And the area is nice and simple. Now we have a simple area. The area is flat, so you could, but the magnetic field is everywhere different. So hence why I wrote the summation of B sub I dot A sub I, because you really would have to do this justice. If you really want to calculate the magnetic flux, we're not going. Don't worry, we're not going to calculate magnetic flux here. But if you really want to do that job, you would have to divide that area, that loop area, into little tiny areas. And you'd have to figure out what the magnetic field was in each place, and it would be a B dot A problem all the way across that area, right? So that's not as simple B times A. Now, he writes in here that it is, but it really is not. So no, the magnetic field vector arrows, I say the magnetic field vector arrows show different directions through the loop. That's what I wrote down. Number 2, what is the magnetic flux through the coil expressed in terms of A and B? Again, I wrote, for me, you want to look at the general formula for that. Again, I'm on number 2 at the bottom of page 1. Again, you know, you might, you know, simplistically, you might say it's A times B, but in reality, those magnetic fields are different. All right, so my answer to number 2 would be that the magnetic flux I picked up a set of pens that I got from Walmart, and I open them up and they're all bad. So kind of on fumes here as far as my pens go. So hopefully I'll outlast this lab. Okay, so I have magnetic flux. So I wrote here, magnetic flux is officially the summation over I of B sub I dot A sub I, okay, or the summation over I of the magnitude B sub I times the little area A sub I times the cosine of theta sub I, where A sub I are the differential areas in which the loop is divided, small enough just to have one magnetic field go through it. Theta sub I is the B sub I is the magnetic field through A sub I. And theta sub I is the angle between B sub I and the normal to A sub I. And that's the flux. And normal is a fancy word for perpendicular to a surface. The area in physics is a vector in the direction that's given by the normal. So again, I would say that phi sub B, the magnetic flux, B standing for magnetic field or magnetic flux, is the sum of B sub I dot A sub I. It's a dot product, scalar product, and that's the sum of B sub sum over I. Now I is a counting number. I'm not dividing all these little areas. Yeah, there's area 1, there's area 2, there's area 3, there's area 4, blah, blah, blah. There's area I, right? So sum over I of B sub I times A sub I times cosine theta sub I A sub I. I mean, there's tiny little differential areas that compose this circular area. Every one of these differential areas, I pick out area I, divides the loop. B sub I is a magnetic field through A sub I. A sub I is so small, there's really only one magnetic field line through it. And theta sub I is the angle between B sub I and the normal to A sub I. I mean, that really is the flux. Some people might tell you, it's just B times A. Well, it'd be B times A if B was absolutely uniform, straight right on through, nice, let's say it was a solenoid. Yeah, then B times A is perfectly fine because it's a solenoid and it's a nice, strong, uniform magnetic field. This is not. This is absolutely not, right? And so again, you don't have a uniform field. So it's not, so things are not quite as simple as it would be, let's say, for a solenoid. Okay, I'm going to page 2. Any questions on this? Take that as a no. All right. Which one causes magnetic flux to change in the coil? I have a question for you guys. Number 3, top of page 2. Which one causes magnetic flux to change in the coil? A or B? Anybody? Kind of a trick question.
Yeah, it sure is.
It's A and B. Magnetic, if you change the magnetic field, you got to change the magnetic flux. If you change the area, you get to change magnetic flux. Like if we have a rotating motor, magnetic flux changes because I'm rotating around the shaft, right? If I decide to have an area and I shrink it, magnetic flux changes. So magnetic flux changes if I change the magnetic field or the area, because the flux is composed of both. If I make a change, the B and A can change. Okay, so I'm going to erase this. Now, this is my number 2. My number 3. Basically, in general, changing A and or B in time changes the magnetic flux. So it's written in a tricky way. You just put or there, but it's actually both. and split throughout this video here. All right. So there are 3. 4. How does the magnetic field change through the coil as the north pole of the magnet moves toward the coil? Is the flux increasing or decreasing? Anybody want to take a stab at that? Move the magnetic field north pole first toward the coil. Is the flux increasing or decreasing? I remember my lecture from a few minutes ago. What happens when I move if I have the north pole face going first, I move toward the loop? Are the number of field lines going through the loop, are they increasing or decreasing? I'm getting more and more through the loop per time as it gets closer, right? So the magnetic flux is increasing, right? So as the north pole of the magnet moves toward the loop, and this is kind of what I said in a moment ago, as the north pole of the magnet moves toward the loop, the more magnetic field lines move through the loop. So more and more magnetic field lines move through the loop. And so the flux is increasing. Magnetic flux is increasing. Area is not changing, but the magnetic field is. All right. So again, you know that when you pull the loop out, you pull the wire out, the magnetic flux begins to decrease. In fact, I forgot to mention this. If you left the magnet, if you actually made the magnet sit still and you moved the loop instead, the exact same situation would happen. So whether you make the loop sit still and you move the magnet toward the loop, or you let the magnet sit still and you move the loop toward the magnet, the exact same thing happens. It all is relative to magnetic flux. So Faraday did both every experiment you can imagine. All right. So number 5 is interesting here. So this kind of goes into this further discussion what we're talking about. So now we're going to try to see this. I'm going to try to talk about it first. Then we're going to see it in the experiment. There's really no numbers really to write down in this experiment. This is a very qualitative type of an experiment. I mean, if we met face to face, it would be quantitative, but this particular lab is relatively qualitative. So, but Faraday's law is a very important thing to understand. So number 5 on page 2, move the magnet toward the loop. Move the magnet toward the coil. And we're going to do this experiment in the software, but I'm going to talk about it first. And observe the deflection of the needle of the voltmeter. Carefully notice the direction of the current as indicated by the voltmeter polarity. Note the conventional current flows from high potential to low potential. A positive reading means the current flows from left to right. The motion of electrons is in the opposite direction to the direction of conventional current. We talked about that. So we need to experiment on how changing magnetic flux, increasing or decreasing, determines the direction of the induced current. Use a right-hand rule for magnetic field to determine the direction of the current. Fill out the following table based on your observation. So we have a table here in the bottom of page 2. Table gives you 4 pictures. So what it wants you to do is it wants you to sketch. So again, the first column says the motion of the magnet. Sketch the magnetic field lines through the coil. Use different color to show induced magnetic field through the coil. You don't need to use different color. I mean, just drawing lines is fine. I didn't use other colors. Anyway, now the second column is going to tell you magnetic flux at the coil due to the bar magnet. increases or decreases, okay? Induced conventional current in the coil, clockwise or counterclockwise, and then the direction of the induced magnetic field due to induced current. Okay, so the second column discusses the magnetic flux that you are causing by pushing a magnet through the loop. The rightmost column talks about the magnetic flux that is induced to oppose you. All right, and then the third column talks about which direction is your current. All right, so let's talk about this. So I'm gonna go to the whiteboard and let's discuss this. And so and then we'll see how we can use the software to verify that what we're seeing is true. So the first picture is as he draws a little loop, and he has a magnet that's going to come in toward it, North Pole first, and it says the North Pole moves toward the loop. Okay, so that means it's moving toward the loop. Well, so first of all, we need to sketch the magnetic field lines. I mean, I didn't do a amazing job or anything. I just we know the magnetic field goes from the North Pole and then you might have some that doesn't make it through here and gets all the way back to the South Pole, for instance. I mean, your magnetic field lines, I mean, these lines that are going through the loop, they're eventually going to come around and come back around and through, right? So all these magnetic field lines are going to make their way back to the magnet. Why? Because Gauss's law of magnetism says that the magnetic flux about a magnetized object is zero. So these just happen to pass through the loop first before they come back around. So some of them don't make it through the loop, some of them come back around immediately, right? So your magnetic field lines are really going to come and look like this, right? They essentially emanate from a North Pole and re-enter through a South Pole. Now, I did not use the word start and stop. I did not use the word generate and terminate or anything like that, because that's what electric field lines do. Magnetic field lines, if you were to actually look inside the magnet, everything forms a loop. Magnetic field lines never start or stop, but they do emanate from the North Pole and they come back around and re-enter at the South Pole. So again, as I am moving toward the magnet, I mean, I'm having magnetic field lines that are going to be going through the loop. Now, number two, well, let's look at, okay. So on number two, I would draw the same picture. Even though the North Pole is moving away, I still have, it's a snapshot in time, whether my velocity vector is moving toward or my velocity vector is going the other direction, I'm still going to have magnetic field lines emanating from the North Pole and coming back to the South Pole. So really the pictures of the magnetic field lines, and you don't even, and honestly, there's not enough room in this picture. You don't even have to even draw these if you don't want to. I mean, you look at, he doesn't give you really much room to draw. So if you just want to draw these, that's perfectly fine. But again, whether the magnet is heading toward the loop or away from the loop, the fact that it is oriented with the North Pole closer to the loop than the South Pole, it's really the same picture. Now, what's happening in column B? All right, let's look at the top row. Again, the magnetic field moving toward the loop. Is the magnetic flux at the coil due to the bar magnet? Is it increasing or decreasing? So this is the case, I'm moving the magnet, North Pole first, toward the loop. You see the magnetic flux through that loop? Is that increasing or decreasing? Anybody want to take a stab at it? So the number of field lines are getting more and more, right? So the magnetic flux is increasing. Because I'm moving the magnet toward the loop, more and more field lines, more and more magnetic field lines. Again, these are, I should label this, these are magnetic field lines. more and more go through the loop per unit time. That means the magnetic flux is increasing. So in this particular case, phi sub B is increasing. Again, I'm looking at the case. I'm looking at row 1. This is row 1 on this table on the bottom of page 2. Again, I'm talking about the magnet moving toward the loop. More and more magnetic field lines are going through the loop per unit time. So the magnetic flux, basically the magnetic field times the area roughly, is increasing. Area stays the same, but the magnetic field lines is increasing. All right, well, for row 2, if I pull it away, is that increasing or decreasing?
Decreasing.
Yes. Magnetic field lines, no, not as many are going through now. I'm taking the magnet away. I'm still oriented North Pole first, but I'm pulling it away, and fewer field lines are going through. So yeah, again, your column 2, your second column on row 2, that magnetic flux that you're causing by moving the magnet, it's decreasing. That's the magnetic flux at the loop. Okay, that's row 2. All right, let's go back to row 1 again. And let's imagine the magnet again coming toward the loop. So we've established that in row 1, where the magnet coming toward the loop, the magnetic flux is increasing. Lenz's law says, oh, I don't like that. That's a change. I don't like change. That's a change where more and more magnetic flux is going through the loop. I want to oppose that change. Means I'm going to create a North Pole going the other direction with my loop. I'm going to create an electromagnet. I'm creating a North Pole going the other direction. Well, how do my fingers go? So again, I'm using my right hand. I'm creating a North Pole going the other direction. That means that my fingers are going to curl. And again, I'm sighting along the magnet. They're going to curl counterclockwise. As I'm looking along the magnet, I'm looking through along the magnet. No, the loop is coming, the magnetic field is opposing, it's coming at me. The current is going to go, as I'm looking at it, counterclockwise. Again, that is as I'm on my eyeball. Not a very good looking eyeball here. My eyeball is behind the magnet. I'm sighting along and I'm seeing what? I'm seeing a counterclockwise current. Okay. So let me ask you this: in the same case, magnet moving toward the loop. I'm looking at the far right column. The direction of the induced magnetic field due to the induced current. What direction is that? So I'm inducing a magnetic field. What direction do you think the magnetic field is going? Remember, Lenz's law wants to oppose you.
So to be clockwise?
It's going to be actually going to the left. Because Lenz's law says counterclockwise is the current. But why am I doing this though? Why am I inducing the current? Because I'm using Ampere's law to basically, because if I have a current going around a loop, Ampere's law says, oh, you have a current going around a loop. You create a magnetic field. The magnetic field, basically I'm creating this counterclockwise current to do what? To create a magnetic field that opposes this change. So the magnetic field is going to be the opposite. So again, your chances are your direct is opposite direction of the bar magnet or the same as a bar magnet. In this case, it's opposite. So again, let's look at this one more time. So I have a magnet heading toward the loop. Okay, so magnet heading toward a loop. Again, if we're prior to chapter 21, we'd have no idea what's going on. So we have a magnet heading toward the loop. What's happening is more and more magnetic flux is increasing. More and more magnetic. The loop does not change area. More magnetic field lines per unit time are going through the loop, which means that magnetic flux is increasing. So Lenz's law says that, well, basically Faraday's law says we're going to induce an EMF. EMF will be induced in the loop. No matter what, this is going to be given as negative change in magnetic flux with respect to time. That's where Faraday's law kicks in. Faraday's law deals with there being an induced EMF. Now you may have a closed loop, which means you also have a current. You may not have a closed loop. You may have what's called motional EMF. Again, if I take a little piece of metal, and I just have a piece of metal flying through a magnetic field, there will be an induced EMF. It's called a motional EMF. You go back to my lectures on this. You will not get a current. You will have what's called a motional EMF. You'll have an EMF no matter what. If you have a closed loop, now you have a current. Just like I have a battery in a circuit, but I have no current unless I close the circuit. Unless I throw the switch, that's when I get the current. But the battery's there. I have that potential there, whether I want to use it or not. Once I close the switch, that's when the current starts going in. So in this case, I do have a closed loop. So then that's where Lenz's law kicks in. Lenz's law says, Lenz's law states that a current is induced to oppose changing magnetic flux. That's what Lenz's law says. Lenz's law is piggybacking off of Ampere's law. Ampere's law states, see, am I still on the, yeah. Ampere's law states that a current in a loop generates a magnetic field perpendicular to the loop. All right, so the number, again, Maxwell's, every electromagnetic theory phenomena, every electric, magnetic, and optical phenomena is an application of one or more Maxwell's equations. So we see here, we have Faraday's law that gets things started. Faraday says, oh, well, there's a change in magnetic flux in a loop. Well, that's an induced EMF. Lenz's law says, oh, it's actually a closed loop. Great. So we have a current. Epsilon equals IR. That's Ohm's law. We have a current now. Great. We have a current because of Ohm's law. So induced EMF with the closed loop, we have a current in closed loop. That means that if there's an epsilon, or I is epsilon over R. That's Ohm's law. All right. So the fact that I have a closed loop means that Ohm's law applies. All right. So then, and again, the idea of opposing change, that's Lenz's law. And the fact is, Lenz's law piggybacks on Ampere's law that says, oh, there's a current in a loop. That generates a magnetic field that is perpendicular to the loop. So all this is going on right here. All right. And so what we have is, again, as I read across the table, I have, again, the row 1, the North Pole first going through the loop. Okay, what's doing that's increasing the magnetic flux. So again, in row 1, the second column will be increase. Magnetic flux increases. And then you say, oh, well, the induced current. Well, Lenz's law now comes into play, right? Induced current says, oh, I want to oppose. So again, I can really answer the far right column first, because Lenz's law says, oh, I want to oppose that change. So my area is not going to change, but you're throwing extra magnetic field through this loop. I don't like that. I want to oppose that. So I'm going to oppose that with a magnetic field going the other direction. And then now I'm going to employ, so that there you are, opposite. That's the far right of the answer, because I need to oppose the change. And then what current does that? Well, I need to piggyback off Ampere's law. So I'm going to have a current that's going to go what? That's going to go counterclockwise as I sight along the magnet in order to make that happen. So as I read across, I have my drawing, and then the second column be increased because why? Because magnetic field lines more and more going through the loop over time. I'm getting more and more magnetic field per time. I don't like that. Lenz's law says I'm going to oppose that. So you're giving me more and more of this magnetic field. I want to give you more of this to oppose you. And how do I do that? Well, Ampere's law then says, well, you get that by having a current going around the loop such that you get that magnetic field that's going to be perpendicular to the loop. All right, so all that's working together. If I switch things around and I say, oh, let's let the magnet move the other direction. The magnet goes the other direction. Okay, so now I'm pulling things out. So my magnetic field is still going to look the same. But now what's happening? Well, now I'm getting less and less magnetic field lines going through. So I'm essentially my second. So I'm on the second row now. My next column would be decrease, because just like Harmon said, fewer and fewer magnetic field lines are going through the loop because I'm pulling it away. Well, Lenz's law says, well, wait, that's a change. I don't like that. I don't like that at all. So you're giving me less of this. I'm going to give you more of this. How do I make that happen? My right hand rule says I want to give you more magnetic field to make up for what's not there. You're taking away. So how that happens? Well, I'm going to now have a clockwise current to make that happen. Again, I'm using my right hand. I'm getting less magnetic field going through the loop. I want to oppose that by making up difference. I'm going to compensate by pushing more magnetic field. And how do I do that? Well, I will have by Ampere's law, I will create a clockwise current to make that happen. So again, so the far right column of row 2 says I want the magnetic field in the same direction. I want the same. I want more of. I'm not getting enough of this magnetic field in this direction. I want more of that. So I want to have the magnetic field that I induce be the same direction. How do I do that? Well, I create the clockwise current. Wait, my finger's bent. Clockwise current. Any questions about that? And again, that's the first 2 rows. All right. The second 2 rows, well, I'm going to move the magnet toward the loop, but this time around, I'm going to switch the polarity of the magnet. I'm going to flip it end over end. I want the south pole to happen first, then the north pole. What's my picture look like now? Well, my picture is going to be magnetic field going through the loop, but this time it's the other direction. The magnetic field is coming in. It originated from the North Pole magnet. So maybe this one really originated from the North Pole magnet going all the way around. But again, the magnetic flux goes through. It emanates from the North Pole and enters the South Pole. So what I have is I have the opposite situation. Yes, I'm approaching the magnet heading toward the loop. What I'm actually doing is, before I was increasing the flux going this direction. The magnetic field is increased going this direction. Now I'm actually increasing the magnetic field going the other direction because the field lines are going the opposite way. The flux is a directional quantity. And so yeah, you're still moving the magnet toward the loop, but what you're actually doing is you're actually increasing the magnetic flux that's going this way, right? Because of the way the field lines orient. And you're going to see more field lines. Why? because you're getting closer and closer, you're going to see more of these fields coming around. If I'm further away, you're not going to see as many field lines. So again, they're coming around the backside, right? And so what does that mean? Well, it means that I'm getting, as I'm moving the magnet south pole first toward the loop, I'm getting more and more of this. And so essentially, I want to oppose that by turning around and opposing it. So I'm going to basically do what? I'm going to meet a south pole with the south pole. And so it means on my north, so if I meet a south pole with a south pole, my north pole is going the other way. So I'm really going to meet a south pole. I'm going to create a south pole with basically I'm creating an electromagnet, and my north pole will be on the other end. So I'm going to get more of this. That is accomplished by what? A clockwise current. So again, I would have an increase of magnetic flux. It's just magnetic flux going the other way. So again, as I'm moving the magnet into the loop, my second column, I'm on row 3. I'm on row 3 here. Sorry. Row 3. In row 3, I would definitely still increase the magnetic flux. Again, it's magnetic flux going the other way, but it's still an increase. I'm getting closer and closer. I'm going to get more magnetic field lines, so it's still going to be an increase. However, the current will be opposite. Why? Because I'm getting too much. I'm getting more and more magnetic flux going the other direction because of the way the magnetic fields are switched. So I need to meet that by opposing it. How do I oppose it? By a clockwise current, right? And of course, what's the magnetic field going to be? It's going to be opposite. Again, I want to oppose the increased flux, so it's going to be the opposite. So really, the row 3 has very similar answers to row 1, except the orientation of the currents. Again, just like I said, Faraday runs his experiments with the south pole first. He's going to see the exact same results, except the orientation of the current. So again, as I read row 3 across, you'd have increase. Why? Because you're having an increased magnetic flux, even though it's going the other way. You have a clockwise current because I'm getting too much of this. I need to oppose it. And I do that magnetic field by making a current that's clockwise. And then again, I'm piggybacking on Ampere's law to do that. And of course, I'm opposing change. So you want to oppose, so you're basically meeting a south pole with the south pole. So again, the far right's opposite. So as I read across on row 3, it'd be increase, clockwise, opposite. So row 1 should read increase, counterclockwise, opposite. Row 2 should read decrease, clockwise, same. Row 3 should read increase, clockwise, opposite. If I look at the bottom row, row 4, basically south pole, again, the same orientation of the magnet, but now I'm pulling it out. While I'm pulling it out, what's happening here is that, well, okay, so what I'm getting is less magnetic field going in this direction, right? Because why? Because the orientation of the field. And so what that means is like, well, wait a minute, I don't like that at all. I want to increase magnetic field going this way because I'm not getting as much. I want to increase that. How do I do that? How do I get more magnetic field going this direction? Well, I create a counterclockwise current to do that, right? And again, the magnetic field, I'm going to meet what? I'm going to meet a south pole with a north pole. So it means I'm going to have south going this way, and my electromagnet that I'm basically inducing is going to be a north-south. So I'm going to be going the same direction. So again, if you read the bottom row, it would say decrease for your magnetic flux that you're creating, counterclockwise for the current that's induced, and the same direction for the induced magnetic field. Okay, so these are some concepts that take some thinking. So before we move on to page 3, do any questions about these concepts?
I can't think of any.
Okay, let's back up what we just said with the software. We talked through it. Now let's see what the software tells us. The software is going to be a little bit hard to see because it's very touchy. So again, it's a lot of theory in this lab and not a lot of like, just reading numbers off the screen. So let me share my screen. All right, so you should see the magnet again. All right, so what I'm going to do is I'm going to do experiment 1. Now let's look very carefully at this. Okay, so what I have here is a current that says, okay, the positive polarity is to the right. Let's take a look how this goes, right? This thing is going left to right. If you look at this, the loop leaving the positive side is going all the way down like so and coming back up. That means that if current was going, if this was a battery where there's a plus side and a minus side, plus would mean that it would be current that would, as I look at the magnet, as I sight along the magnet, it would be what? It would be clockwise current, right? It would be current leaving the positive side, going on down. Again, imagine your eyeball right behind the South Pole, going on down, coming back up. So a positive polarity in this picture would say that would be a clockwise current. On the other hand, if it was going the other direction, that's a negative polarity. That would be things going the other way. Again, positive basically means the positive battery is here. So if I let this to its own accord, current would want to flow this way. If current flowed the opposite way, that would be negative. And then what would that correspond to? That would correspond to a counterclockwise current. All right. So again, the thing to remember here is that positive should be clockwise, negative should be counterclockwise. Now let's see what happens when you may see this, you may not see it because it's very touchy. I'm going to try to run this magnet into the loop and see what happens. I said counterclockwise, so I should see a negative deflection if I'm correct. This didn't work. All right, there we go. Negative deflection. I don't know if you saw. Do you guys see that?
Yes, we do.
Awesome. So that's a negative deflection. You notice that, and again, it only mattered when I moved the magnet. I'm not moving the magnet anymore, but the fact that it deflected negatively means that was a counterclockwise current. So that was Lenz's law saying, I don't like that. I'm gonna pose this with a magnetic field going to the left, which would require me, if I point my thumb along the left and I use my fingers, that's a counterclockwise current to make that happen. Counterclockwise in this setup means negative. So yeah, we saw that. If I pull the magnet out, I should see a rightward deflection, which would mean a clockwise current. So let me see if I can make this happen. Yep, there you go. You should have seen a rightward deflection. Hopefully you did. Anybody see that?
Yes, yes, I did see that.
Awesome, cool. All right. I never know what you guys are saying. This software combined with Zoom, interesting things happen. So
It takes me a minute to unmute.
Oh, that's okay. Don't worry about it. So that's row 1 and row 2. Row 1 and row 2 basically confirmed what we talked about. Now let's do the following. Now I'm gonna go to the bar magnet, and there's a button that says flip polarity. I'm gonna click that button, and what it's gonna do is I'm gonna have the south pole going first. Now, south pole, I should see everything being the same. I should see a clockwise current. Clockwise should be a positive deflection. If I'm correct. Positive deflection, great, that agrees. Only when it's moving, and I pull it out, should be counterclockwise in agreement with my table. And there it is. So negative deflection. So again, as you saw, this is the experiment that Faraday did without aid of a computer, of course, to show us the Faraday's law. Okay, so again, we just did. So now I'm on page 3. Now decide if the induced magnetic field is going to increase the flux through the coil or decrease the flux through the coil for each case. Tabulate your results. So again, I think we can take the information we just got done. This is a little bit of a redundant table, I suppose, but so we're saying it's the motion of the magnets on the left. Again, we're going to go through the 4 cases again in the far left corner. I'm on the top of page 3. Magnetic flux at the coil due to the bar magnet. Okay, does that increase or decrease? And the induced magnetic field, does that increase or decrease? All right, and so, the induced magnetic field increases or decreases the flux of the coil. All right, so again, read this carefully. The magnetic flux at the coil due to the bar magnet increases or decreases. Okay, that's the first question. We've already kind of talked about these. Then the right column says induced magnetic field increases or decreases the flux at the coil. So let's be very careful in our thinking. So the first column is ones we've already answered. So if I look at the first case, the north pole is moving toward the coil. We have decided that increases the magnetic flux. So then that would be increased. So it increases the magnetic flux. And again, we've said that before, but the north pole moving toward the coil, that increases the magnetic flux. Now, here's the question you have to think about more. The induced magnetic field that results from this, does that increase or decrease the magnetic flux? What does the induced magnetic field want to do? This is from Lenz's law.
It wants to oppose it, doesn't it?
Indeed. So it wants to work against you. So if you're working to increase the magnetic flux, it says, I'm going to work to decrease the magnetic flux. So I'm going to work against you. I'm going to decrease it. So the far right column should be decrease. The induced magnetic field that Ampere's law gets from, because of Lenz's law, works to decrease that. It wants to work against you. If you look at row 2, well, if we move the north pole away, we all decided, yes, that effectively decreased the magnetic flux. What does the induced magnetic field want to do?
Increase.
Increase, work against you. Whatever you're doing, I'm going to do the opposite. South pole moving toward the coil, we said that increases the magnetic flux. It's the magnetic flux going the other direction, but it's still magnetic flux. And so the induced magnetic field will seek to decrease. And again, it wants to work against you. And then the south pole moving away, well, that decreases the magnetic flux. Just again, magnetic flux going the other direction. Does the induced magnetic field want to increase or decrease the flux? Wants to increase, right? Wants to work against you.
On number 4 on the last column, yes, it's increase.
Yes. So if I read the 4 rows, number 1, left to right should say increase, decrease. Number 2 should say decrease, increase. Number 3, left to right, increase, decrease. Number 4, left to right, decrease, increase. They oppose each other. Again, all that really says is Lenz's law seeks to oppose whatever it is that you're doing. It's a law of opposition. You don't get something for nothing. Number 7, Lenz's law explains how to find the direction of the induced current. Note that the induced current wants to, quote unquote, oppose the change in flux, right? How do your observations summarized in number 5 and number 6 either agree or disagree with Lenz's law? Well, I said, well, the observations number 5 and number 6 above corroborate Lenz's law, and that each case the induced EMF induces a current that creates a magnetic flux by Faraday's law that opposes the change in flux that caused that was caused by the moving bar magnet. All right, so I'll write that down. It's a lot of words. So let me go back to the whiteboard. So again, this lab really wants to hammer Faraday's law into you. So again, it is, I would honestly say it's, I mean, there's toward the end of physics 1, I told you one of the most important equations in all of science was, I don't know if some of you guys had in physics 1, some of you didn't, but if you remember the famous entropy equals the Boltzmann constant times the natural log of the number of ways, number of microstates. And this is the connection between statistical mechanics, the actual atomic physics that's that's inside of a let's say a volume of gas, and this the link to thermodynamics. This is entropy, and that gets the regular thermodynamics variables, entropy and temperature and internal energy and that stuff, right? That's the equation by Boltzmann. Boltzmann has that on his epitaph. One of the most beautiful and important equations all in history. I would put Faraday's law right there. Faraday's law is another one of these, boy, oh boy, these F equals ma is another one. Just equations that shook the world, right? Those are, so Faraday's law we're studying tonight is one of the equations that shook the world. This is one of the most important equations in all of science, right? So it's important. It's important to have a lab that really focuses on this very important law. So I said for number 7, I said the observations in number 5 and number 6 above, again, they're right above what we just got there doing, corroborates. I like that word. Lenz's law. In that, in each case, the induced EMF from Faraday's law induces a current that creates a magnetic flux that opposes the change in flux caused by the moving bar magnet. By Lenz's law, if you will. Lenz's law that's the negative sign in Faraday's law. And really nice. 1831 is Faraday's law. 1834, Lenz's law. So they right after each other. And 1870-ish was Maxwell's theory. So everything kind of was set for Maxwell. Nobody really knew how everything fit together. All right. Number 8, consider the claim that, quote, according to Lenz's law, induced magnetic field opposes the magnetic field of the bar magnet. Do you agree with this statement? Explain your answer based on your observations. I mean, I state that this is not a statement of Lenz's law. Lenz's law states that an induced EMF appears in the loop to generate a magnetic flux to oppose the changing magnetic flux caused by a moving magnet. I mean, Lenz's law discusses, it talks about magnetic flux, not necessarily magnetic field. It might be magnetic field in our case. If we talk about a motor, you're getting the flux. The magnetic field in that case is constant. What's causing the change is that you're rotating about a shaft. So the area orientation is what's causing the change there, not the magnetic field. Magnetic field in that particular case, your motor is constant. So maybe I'll write that down too, I guess. Again, these are fairly heavy ideas. All right, so if you kind of feel a little overwhelmed, that's okay. I mean, these are ideas that first time you look at it, you really have to think about these, because these are electromagnetic theory is not for the faint-hearted. All right, number 8. So again, I wrote down this is not a statement of Lenz's law. Lenz's law states that an induced EMF appears in the loop. To generate a magnetic flux to oppose the changing magnetic flux caused by the moving magnet. All right, so this is not a statement of Lenz's law. Lenz's law states that an induced EMF appears in the loop to generate a magnetic flux to oppose the magnetic flux caused by the moving magnet. I mean, you can state that differently if you wish, but again, that's what I would write. Okay, so again, that is more or less Lenz's law. I'm on page 4. Number 9, we start talking about Faraday's law particularly. Now select the light bulb as the current indicator in the circuit. Move the magnet back and forth through the coil at different rates and observe the variation of the brightness of the bulb. According to Faraday's law of induction, the rate of change of magnetic flux through the coil is proportional to the voltage induced in the coil. All right, so let's take a look and see what we can see here. So again, I'm going to go back to the lab, and now we're going to pick the light bulb option. Again, we do this face to face as well, so you're missing some good stuff thanks to the lovely COVID. All right, I'm going to share my screen. All right, so we're going to do here, you guys see my magnet again?
Yes, I can.
Awesome. I'm going to flip the polarity. Kind of give us what we had. There we are. Boy, it's really slow. All right, now instead of the voltage indicator, we're now going to select the light bulb. So sometime between now and Christmas, here we go, the light bulb. Now, what we should see, now remember what I told you, is I have to do mechanical work, or I have to have mechanical power in order to be able to move that magnet in the loop. The loop is going to oppose me by making a magnetic field, or that's going to oppose me. So, but that induced current will dissipate the same amount of power with I squared R heating. So I squared R, well, we know that we have, let's say an appliance hooked up to a circuit, that the appliance acts as a resistance. So if you have a light bulb, well, the I squared R should actually go into lighting up the light bulb. So let's see what happens. If I move the magnet slowly, there it is. There's a light bulb, turns on. Let me move it a little tiny bit, see what happens. Light bulb should not go, the light bulb doesn't go as much. I'm gonna move it a large amount. Nope, not so much. Okay, I'm gonna try to pull it out quickly now. I should see it, yeah, well, big light bulb there. So again, the light bulb is going to, because there's an induced current, the light bulb lights up. That's that I squared R power dissipation that's equal to the mechanical power that I'm employing to move the magnet in and out of the loop. The two are equal by the conservation of energy. There's only two ways of inputting or exiting energy from the system. There's only one way to input energy in the system. That is through mechanical power. And there's only one way for energy to leave the system. That is through heat dissipation, or I squared R thermal energy dissipation. There's only two ways: one way in and one way out. Okay, I mean, so again, you know, different systems have different ways of managing energy. For this situation, the only way energy goes into the system is through mechanical work. The only way energy leaves is through I squared R. Okay, so we have mechanical power to put energy into the system. Thermal dissipation, I squared R heating to get it out of the system. So number 10 then says, why does brightness of the bulb change when you move the magnet through the coil at different rates? Explain your answer with Faraday's law and electrical power. All right, so again, this takes a little bit of thinking, but let's see. Back to the whiteboard. This kind of goes into what I talked about earlier on, is that Lenz's law is a statement of the conservation of energy. All right, and so now there's not a lot of space to write stuff here. I mean, the explanation I had required as much space as I could possibly muster, but I said something like this in number 10. Homework special. All right. I said something like Faraday's law states that an EMF epsilon is induced in a wire loop. Due to a time varying magnetic flux. According to epsilon is negative, delta phi sub b with respect to t. Again, phi sub b is the magnetic flux. Again, phi, remember, is the Greek letter phi, right? PHI, phi. It's Greek. Like I think it's a Greek F. Anyway, epsilon is negative, delta phi sub b with respect to t. The induced EMF epsilon in the loop induces a current I. Okay, and then since the loop has a resistance R, everything has a resistance unless you're a superconductor. Since the loop has a resistance, and it could be the light bulb too, maybe most resistance in the light bulb, R, The mechanical power in moving the magnet through the loop equals the dissipated power I squared R I'm still on the screen here. I squared R, that is demonstrated by the lit light bulb. All right. So, I mean, again, I'm a little on the wordy side, but Faraday's law states that an EMF epsilon is induced in the wire due to the time-varying magnetic flux according to epsilon equals negative delta vis-a-vis with respect to t. The induced EMF epsilon in the loop induces a current I. It's a closed loop. Since the loop has a resistance R, the mechanical power in moving the magnet through the loop equals the dissipated power I squared R that is demonstrated by the lit light bulb. So again, the fact the light bulb lights up is that there's power being dissipated. Okay, you can actually run a light bulb with this. And we do, the light bulb in your house, what's lighting up your computer right now is Faraday's law. So it's not just the amazing thing to see here. I mean, you see it everywhere you look. All right. Any questions about that?
Not so far.
Number 11, you have already realized the magnetic flux changes as you move the coil back and forth. What caused the rate of change of magnetic flux in this situation? Again, the rate of change of magnetic flux deals with the magnetic field lines going through it, right? And so you might say something like this to number 11. And this is a very theoretical lab, so I'm kind of helping you through it. There's a lot of deep thoughts in this lab. So 11, I would say something like this. The magnet moving back and forth causes a change in the number of magnetic field lines passing through the wire loop. Okay. Which causes a change in magnetic flux through the loop, which causes a change in magnetic flux through the loop. Since B sub E is the summation over I of B sub I dot A sub I. All right, so again, you move the magnet back and forth. That causes a change in the number of magnetic field lines passing through the wire loop, okay? And that causes a change in magnetic flux because you're changing B, and magnetic flux is given by, in general, by summation of B sub B is summation over I, B sub I dot A sub I. I don't just say B times A because as I said, I know that the magnetic field is not uniform. As you see, the magnetic field vectors are constantly changing. All right, Roman numeral 3 is the electromagnet with a variable current. That's the final part of this lab. Any questions up till now? All right. All right, we have a new setup. Let's see. I'm on the bottom page 4. Now select the transformer tab, and let me go to the lab again. Share my screen. Let's see. All right. All right, you see the magnet and loop again? Anybody? Armin?
Yes, I can see it.
All right, very good. I just want to make sure I'm projecting the right thing. I've in the past, I've talked a whole bunch and people weren't seeing the picture I was seeing. So
No,
right.
You're good. You're good.
Verifying. Let's see, electromagnet. Okay, so reading this, bottom of page 4. Now select the transformer tab. So we're going to leave the pickup coil and go to the transformer. All right, so transformer tab, you have 2 coils. Okay, you'll see this eventually, I think. You have 2 coils, one with an AC current supply, alternating current, which direction the current changes, plus or minus, directions in form of a sine wave. And the other one is the pickup coil. Set the simulation as shown. Oh, here it is. Oh, it took a while. All right. So this is the AC, the alternating current coil that has, that you see the electrons moving in it. And of course, we saw the pickup coil previously. That was in the, that again, that's the same kind of coil we saw before in the previous set of experiments. Now run the simulation, observe how the magnetic field and the voltage change as the alternating current runs through the electromagnetic changes. Change the strength of the AC current by moving the vertical slider up and down. Use a horizontal slider to change the frequency of the AC source. Use 100% strength and 100% frequency. So we're going to set up essentially what we see in the picture, all right? And so let me see here. I'm going to 100% strength and 100% frequency. Again, that's the AC. So let's see here. Okay, what you see here is DC, right? We want to select AC. All right, so AC is a button, and so now we have now we have alternating current that's going to be causing change. I want to, this side right here is the, let's see, that's the 100% strength. And then here we have 100% frequency. So we're going to increase the frequency to 100%. So these little green lights, which are very hard to read, are indicators. So they both say 100%. Increase the strength and the frequency. Okay, and I basically want to do is, I don't want this light bulb here either. I want to actually have the voltage indicator. And I really want to do is I'm going to just for the moment put this down to 1 loop on the pickup coil. So the bottom portion here is the pickup coil. And I want to maximize my loop area for the time being, make it as big as possible. And I really want to stick this little loop inside the big loop. And then we would be doing this exact experiment in the face-to-face. So what you're seeing here is I'm going to try to place it carefully. I'm placing the little loop that's alternating in time. I'm going to try to stick it right in the middle of the big loop. And I want to try to make it so it's kind of symmetrical here. All right, that's probably as good as I'm going to get. And you notice that the there's a back and forth motion of the voltage reader. It's going back and forth, back and forth. And really, we obviously have zoom and we have other effects happening here. So if the way it's supposed to work, it's supposed to be going back and forth, in accordance with the frequency. It should be going the same frequency as what you're seeing. But anyway, you do see that arrow going back and forth. Now I'm on top of page 5. Explain why a time varying voltage is induced in a pickup coil. So let me ask you guys, why do you think that voltage reader, and the voltage reader is connected to the pickup coil? Why do you think that voltage reader, that voltage indicator is going back and forth? What's causing that to happen? So the voltage reader, right? That's going to tell you if there's an EMF in the pickup coil. All right. So again, the pickup coil does not have a battery. Pickup coil is just a coil, and it has a voltmeter attached to it. Now, there has to be a changing magnetic flux for there to be an EMF. In fact, the magnetic flux is always changing because inside of it, we have magnetic field that's basically always varying because of the AC generator or the AC coil. So let me kind of draw a little bit of what's happening here. So what we have is, and this is kind of like how our electricity works. So we're seeing a coil within a coil. Okay, so on the outside you have the big coil. In the big coil, there is a little voltage reading device, right? And again, there's no battery in this coil, so there should be nothing to read. And of course, you know, the voltage, again, the current is either going to go one direction or the other. So there's a polarity associated with the voltage as we discussed earlier. But inside of here is really another coil or another set of coils, right? Now, what's happening here is that you constantly have back and forth motion. So again, this is an AC generator. So it's going to be constantly back and forth motion. It's going to be going clockwise, counterclockwise, clockwise, counterclockwise, back and forth, right? Sinusoidal. And what's going to happen here is that we know from Ampere's law that there's going to be a magnetic field that's going to be, you know, it's going to be either going one way or the other. But we have from Ampere's law states that there'll be a time. Ampere's law states that the time varying current, or whether it's a time varying or not, right? You know what? I don't have to. It could be a steady state current, right? It states that the current in the loop induces a magnetic field perpendicular to the loop. All right, so this little loop inside here, it has a time varying magnetic field. When the current is going this direction, you know, so let's say clockwise as written, well, the magnetic field goes this way. Magnetic field goes to 0. And when the current decides to go the other direction, the magnetic field goes the other way. So it's this way, 0, this way, 0, this way, 0, back and forth, back and forth. You have the magnetic field. That's creating a change in magnetic flux. Okay, so when I calculate the magnetic flux, on the other hand, for the big loop, well, what do? Well, I divide the loop's area into all these little areas, some of which are going to coincide with the inside coil, and some of which will not. And I'm going to do the B dot A, or I'm going to do the flux. Well, a whole bunch of it's going to be 0 for the portion where there's no magnetic field. And for the portion where there's magnetic field, it's going to be non-zero. But anyway, look at, there's going to be a flux through this loop as well. The fact that there's a flux through the loop right here means there's going to be a flux through the big loop. The fact that you have a changing magnetic flux through a loop, like this loop, means you're going to induce current all the time by Faraday's law. So here you're inducing current for whatever reason, because you're attached to a power supply. And because you're inducing current, what happens? Well, because you're inducing current, you have magnetic field that's going to be generated by Ampere's law. Ampere's law is at work here. But that magnetic flux, you have a coil within a coil. That magnetic flux is also within the big coil, which is giving you a change in magnetic flux to the big coil too. Faraday's law sees that. And that magnetic flux induces a counterclockwise or clockwise current, basically a time-varying current out on the big coil. Faraday's law is going to induce an EMF. So it's going to be an EMF induced, and because you have a closed loop, Faraday's law is going to induce a current. So on the outside loop, you're going to have time-varying currents. You're going to have the time-varying, and hence you're going to have a changing of polarity all the time. Faraday's law is going to show you a change in polarity. So that's why your indicator is constantly going back and forth, because you have this change in polarity. All right, and so that's what's happening. You have yes, there's magnetic flux through here. There's also magnetic flux. This area happens to be part of the overall area of the big loop. And yes, technically, that is magnetic flux through the big loop too. Okay, so deep concept. Is everybody on board with this? I mean, it's very beautiful. I mean, all this works together. So, I mean, it's beautiful to me at least. Okay, so now number 12 says, explain why the time-varying voltage is induced in the pickup coil. So I'll kind of put some words into what I just got done saying with a picture. Picture's probably more useful than my words, but so I wrote quite a bit here for number 12 because there's a lot going on. So number 12 is saying, well, it says, explain why time-varying voltage is induced in a pickup coil. Well, the loop with alternating current. Induces a time-varying magnetic flux in the loop. We'll say in its loop, the internal. Okay, so since the alternating current loop is placed inside the pickup coil, I actually never heard of the term pickup coil before. I don't know if that's a typical term that's used, but it's the alternating current loop. Is placed inside the pickup coil. The magnetic flux in the pickup coil also changes in time. with the same frequency as in the AC coil. AC meaning alternating current. Okay. Faraday's law induces a time-varying EMF in the pickup coil. Which we are observing with the voltmeter applied to the pickup coil. That's why it's going back and forth. So what I drew in that picture, you know, picture's worth 1,000 words. The loop with alternating current induces a time-varying magnetic flux in the loop. Again, that's really by Ampere's law. Since the alternating current loop is placed inside the pickup coil, the magnetic flux in the pickup coil also changes in time. Again, it shares the area. With the same frequency as in the AC coil. So again, the same frequency. Faraday's law induces a time-varying EMF in the pickup coil. Because you have this change in magnetic flux in the pickup coil, Faraday's law causes a time-varying EMF. And that's what we're observing with a voltmeter applied to the pickup coil. I mean, again, you're also seeing the back and forth current. All right. Any question about that? I'm going to go to 13. What we're going to do is we're going to look at, do the best we can to look at the, we're going to go back to the lab. And we're getting pretty close to done here. Let's see. Go back to the lab. Share my screen. Okay, so we should see the coil stuff again. Now, number 13 says, make sure that the electromagnet with 4 loops, okay, the inside one, is symmetrically placed at the center of the pickup coil. Tried to do the best I could there. Now with 100% AC strength all the time. So again, the AC strength is 100%, yes. Now, to get good consistent observations, keep the setting for the rest of the observations. This is very important. Okay, sure. We will change the frequency of the electromagnet loop area of the pickup coil and the number of loops for the next set of observations. Observe the maximum voltage generated in the pickup coil each instant below. Record your observations. Consider the least count of the voltmeter as 1 unit. Again, there's a few typos here. The maximum voltage reading of the voltmeter is 20 units. Voltmeter shows proportional readings, but not exact results, not exact volts. So if you look at this voltmeter carefully, you see kind of like major, there's a center, and then you see kind of major increments, and that's really 5, 10, 15, 20 as you read down. All right, and so right now we're looking at going back and forth. It looks like plus or minus 4. Not quite reaching that big increment. So it's really hard to kind of read it, but right now the way it's set up, it looks like plus or minus 4. So right now I have it at maximum frequency. And so I think it's a lot easier to do all the max frequency measurements first, and then we'll set it to the 50% frequency. Okay, so let me do all the max frequency. So the first thing I want to do, if I read the left column, I want to keep the internal AC coil at 4 loops all the time. What I'm varying here is the number of loops in the pickup coil. And so row 1 is going to be 1 loop in the pickup coil. Row 2 is 2 loops, and row 3 is 3 loops. So right now I'm on row 1, and I'm looking at the maximum voltage, and let's see, I'm reading this as 4. So I would actually write down, I don't know why he wrote 3, 6, and 8 in that second column. I'm not really sure, but I would write in that, so the left column tells you number of loops. The middle column is the plus or minus voltage, if you will. So I'm looking at this and I'm seeing it as about plus or minus 4. So I'd put 4 there, 4 volts in the first row, middle column. All right. And then I'm going to increase the number of loops. So I'm going to increase, again, I'm going to the bottom section of the pickup coil. I'm going to select, I'm going to hit the up arrow and select it to 2. Now I have 2 loops. Notice what happens now is that now the back and forth, the voltage is actually varying in a larger way. It looks like it's going plus or minus, looks like plus or minus 8 to me. And that's with 100% frequency. So I'd probably write 8 in that middle column. And then if I go to increase the number of loops one more time, again, I'm just doing the middle column right now. I take the loops back to 3, or up to 3 now. Now you should see 3 loops. And now it looks like the voltage is reading plus or minus, looks like 12 to me. Yeah, plus or minus. So I'd put probably 12 volts right there. So my middle column would probably read 4, 8, 12 as I'm reading top to bottom. Now I'll tell you why I'm doing it this way, because it's really hard to mess with this frequency slider when these loops are in a way. So I'm going to get these loops back down to 1. And now I'm going to take the frequency slider and I'm going to take it as best I can to 50%. And again, I'm probably going to have trouble with that. If I'm not careful, I might accidentally grab the pickup coil and move it. So I'm trying to avoid doing that. This is a little bit of a clumsy software setup. And I messed around earlier today, and I kind of got in the way of the pickup coil, and I moved the pickup coil instead. So let me see if I can just grab the switch and not the coil. 67%. See, I just moved the coil. That's what I was afraid of. All right, well, while I'm at it, I'll try to move the coil back. So the whole point is you want to have consistent experimental results with the stupid coils in the way. I'm at 50, 55, but that's probably as good as I'm going to get. Let me try to move the coil back. I had it. That's probably as good as it's going to be. And so you notice that, I mean, it's around 55%. I mean, I'm not going to mess around to get 50%. It's too touchy. But you notice that I'm at 50% frequency. Now I look like I'm going about plus or minus 2 volts. So I probably just write in the far right column on the first row, I'd probably write 2. Because it's not as big. I mean, I'm at 50% frequency, it's reduced. Now let's look at 2 loops. So I'm going to hit the increase up to 2 on the number of loops in the pickup coil. And now it's 2 loops, and now I'm going to go, it looks like plus or minus 4, maybe plus or minus 4. It's going kind of slow too. I mean, again, the frequency is slowed down. Maybe 5. Maybe 5. So maybe the far right column on the second row might be 5. And then if I go to 3 loops, That looks like maybe 7. So the far right column might be, for instance, 2, 5, 7, as I read top to bottom. Okay. So, I mean, again, you can judge it with your eyes better as well as I can. But again, you're seeing a behavior that's based upon changing a number of loops in the pickup coil. Well, explain. So number 14 says, explain why does the induced voltage change with frequency? Okay, so again, let's understand that. Why does it change with frequency? So I'm going to erase this. I need to reorient my computer. Sec. All right. So why does the induced voltage change with frequency? Well, as explained in 12, that's why I said I kind of talked a lot about this number 12. Right, so 12 is what we're on 14 now. Voltage is induced by Faraday's law. Right, Faraday's law is epsilon is negative delta phi sub E with respect to T, right? And so because of the time varying magnetic flux in the pickup coil, caused by the time varying flux in the AC coil. So understand this is a temporal equation. This is a time-dependent equation. So what this is telling you is that it depends on the rate of change of magnetic flux. If you're changing the magnetic flux more frequently, you're going to have a larger EMF, right? So, if the magnetic flux changes more frequently, because it is a time-dependent equation, the induced EMF increases. I mean, it's like the first experiment. You know, if I move the magnet faster, the EMF increases. Why? Because I'm changing the magnetic flux faster. Magnetic field lines are going through it faster. Here, I'm changing the magnetic field back and forth because of the time varying current. If I make the current go faster, I make the magnetic field change faster. That means the magnetic flux changes faster, and that means that change is going to be recorded as a larger EMF by Faraday's law. So indeed, the frequency does make a difference. The faster you make a change of the magnetic flux, the greater the EMF that's induced, the greater the currents that are induced. Right. So again, this is equivalent, like I say, of the moving the magnet faster. Any question about that? That's
No, I
14.
can't think of any.
Okay, that's 14. 15. And it's a very theoretical type lab. 15 says, why does the increase in the number of loops increase the induced voltage? Well, remember, what I just wrote down was really not the complete Faraday's law, but remember, Faraday's law is actually epsilon is negative cap n delta vis-a-vis with respect to t, right? Not just delta vis-a-vis respect, not just negative delta vis-a-vis respect to t, but it's also the number of loops. So the induced EMF in the pickup coil is directly proportional induced EMF in the pickup coil is directly proportional to the number of loops n in the pickup coil. So that n is the number of loops in the loop that where the current's being induced. Okay. Again, so the more loops, every loop is going to have a current I going through it. So they add up. These are, and we talk about inductance, these are called flux linkages. Every one of them contributes a delta vis-a-vis with respect to t. So every one of them, you just basically add them all up. You get n of those. Well, you have n times the delta vis-a-vis with respect to t. You have n times the EMF. Everyone contributes. And so again, number 16 is pretty easy. That one says, write down the Faraday's law to account for the number of loops based on your data. Well, 16 literally. So again, I wrote that in 16. Literally, all I wrote was that. Kind of repeat a little bit, but again, Faraday's law. That's what it is. That accounts for the number of loops. That n. The n is a counting number that just counts the number of loops. Any questions? I'm about to turn to the last page, page 6.
I'm right there with you.
Excellent. All right, I'm on the top of 6. I'm looking at 17. Let's see what this says again. Now keep the number of loops to be 3 and decrease the area of the pickup coil to 20% of the original area. Set the frequency to 100% frequency, run the simulation and record the maximum value of the induced voltage. Compare this maximum value with the previous result you got with 100% frequency and 100% area for the 3 loops. So let's remind ourselves with the 3 loops, 100% area, 100% voltage. Let's go back to the lab. All right. So again, we're going to be looking at flux with the the area changing now. So let's go back and share my screen. Okay, there we are again. Now, I have, let's see here. I want to do 3 loops. That's what I have. And I have 100% area. Let me read this again. Now keep the number of loops to 3. Okay, the number of loops is set to 3. Good. And decrease the area. Okay, we're going to decrease the area. So, okay. We're going to look at it for 100% area and 100% frequency. All right, so again, let's take a look. I need 100% frequency. That's the problem. Go mess with that thing again. All right, so I'm going to reduce it down to 1 for a moment. Gotta get that frequency back up. All right. See if I can not move. Just want to grab the frequency slider. There it is. Look at that. Sweet. All right. And 100%. All right. Now we will set the number of loops back to 3. There we are. Okay. Let's go get ourselves a reading real quick for 3 loops. And I mean, again, I'm just because I've moved the thing around a little bit. Okay. So if I look at, so again, I have a little table here that just has two spaces to enter. The left column is for 20% area. The right column is for 100% area. So I'm going to I kind of want to get myself a new area for 100%. So that voltage looks like it's going plus or minus. It's like it's like 12. So it's going plus or minus 12 to me. Yeah. So I'd probably write with 100% frequency, the right space, I'd probably write 12 volts in the right space, right? That again, that's 100% area, 100% frequency. Now I'm going to take the area down to 20%. So there's a slider that talks about the pickup coil, and the area right now is set to 100%. I'm going to slide it over to look like it's at 20%. Let's see what happens now. Now I've reduced it. I really made the pickup coil smaller. What's happening to my voltage now? Boy, what is that number? That's 10. It's like 15. So that far left column is like 15 volts. So the right column, I think, was 12 volts, and the left column is 15 volts. So I've been by reducing the area, I've actually increased the EMF. Now, why would that be? Well, remember, before we had that little coil in the middle was just a small portion of the area of the larger coil. So the EMF, there's a magnetic field because of the time varying magnetic. So the time varying current in the alternating current coil in the center of this loop, it's varying in time. It's varying the magnetic field. That magnetic field is causing a flux. Now that's certainly a flux. That magnetic field is caused by Ampere's law. Okay, and then because the that loop is at the center of the bigger pickup coil loop, Faraday's law considers that as a flux through that loop as well. And so again, you get an induced EMF and hence an induced current in the pickup loop, the large pickup loop, caused strictly by Faraday's law. And of course, we'll get so that flux causes an induced current. Now before we had the AC coil was taking up a small portion of the area of the loop. So when you want to go calculate the flux, you're calculating a bunch of zeros. You're only calculating non-zero flux for the area, the small area that was shared between the big pickup coil and the smaller coil. But now you squinched it down so that now they're about the same area. The pickup coil and the AC coil are about the same now. So all that flux is going to count for everything. There's going to be very little zero that you're going to calculate in the flux calculation. So I'll write this a little paragraph here to kind of say what I just to talk about what I said. You have so when you're calculating the magnetic flux, you have a lot less zero that you're calculating now. All right, and so the B dot A. Well, the B dot A for the portion of the pickup coil that is not where the area is not shared with the smaller AC coil. You do B dot A right there, you're going to get zero because there's no B. There's only A, right? So how would I answer 18? I'd say something like this. Why does the area matter? Smaller pickup coil area. Well, the only area that matters The only area that matters in the flux calculation is the portion of the pickup coil occupied by the AC generator coil. Since there is only flux in this region, since there is only magnetic flux through this region, reducing the area of the pickup coil increases its flux. Since the proportional area occupied by AC generator increases. Therefore, by Faraday's law, the EMF induced in the pickup coil is enhanced. All right. So again, I said something like the only area that matters in the flux calculation is a portion of the pickup coil occupied by the AC generator coil, since there is only magnetic flux through this region. So again, in the beginning, it was only a very relatively small region. Most of the calculation of the flux in the pickup coil, the majority of it was in regions that was not having magnetic flux. So you're just getting B dot A. All those B dot A's were zero because the B was zero there. But now you reduce the area of the pickup coil, right? So reducing the area of the pickup coil increases its flux, since the proportional area occupied by the AC generator increases. Therefore, and that's really AC generator coil. Therefore, by Faraday's law, the EMF induced in the pickup coil, induced in the pickup coil is enhanced, right? And so again, almost all the area now is flux. There's no more zeros to calculate. And so again, since Faraday's law is epsilon equals negative delta phi sub b with respect to t, because you get bigger phi, you're going to have a bigger epsilon. All right, last question, number 19. I'm going to ask you guys to help me on this. So, kind of like what you just got done seeing. See if you're designing a situation, if you're designing something like this, how would I? So it says number 19 says discuss possible ways to increase the induced voltage in the pickup coil. So if I have this pickup coil and I have the AC generator inside of it, I mean, I found a couple of different ways. What are some ways that you can actually increase the voltage in the pickup coil? Again, hint, we just got done talking about one of them. What do you think? I have this set up and I want to increase the EMF. I want to increase that voltage that I see in the pickup coil.
Well, we reduced the area.
Indeed, that's one of them. Reducing its area is demonstrated by 18. Very good. So I got 2 bullets. There's probably more. So I said we can increase the voltage of in the pickup coil by I was tired this morning, so I got 2, maybe there's more. Reducing the area, reducing its area. As demonstrated, number 18, and this is number 19. As demonstrated in number 18. Can you give me a second one? So let's look at Faraday's law. Faraday's law is epsilon equals negative, cap n, delta phi sub e with respect to t. Actually, I just thought of a third one. So looking at Faraday's law, while we're able to reduce the area by increasing the flux that way, anything else in that equation that can cause you to have a larger epsilon? What if I increase the number of loops? That'll do it.
Sure.
So increase the number of loops in the pickup coil. Anything else that might come to mind? You had to engineer one of these things. How about the frequency? If I make,
you could increase the frequency.
yeah, if I make the frequency go bigger, I change the time rate of change of the flux. I increase it, make the flux change faster, get more epsilon. So again, look at one way to always answer a question is always to ask yourself, do I know an equation that I can look at? Yeah. So what can I vary in this equation? So we can increase the frequency. The AC coil. Those are 3 ways to get a larger EMF induced in the pickup coil. And that's all I have, unless you have any other questions. That's the lab. Any questions among the 3 of you who are left?
Dr. O'Callahan, I can't think of anything.
All right. Allison, Michaela?
No, I'm absorbing as best I can.
All right. Well, you got the video. I put this as a video.
Yeah. Thank you
So,
for tonight.
You betcha. So this will be on YouTube, and so I'll give you a link to it. And so if you want to look at some of the things I said, you can look at it on your own time a little bit more if you like.
All right.
Thank you.
You betcha.
Thank you.
Have a good one.